All right. Next up, I'd like to welcome Brittany Johnson from the University of Washington.
All right, good morning, everyone. I'm going to talk to you a little bit about the Green Ridge Fire, so probably not a fire we've heard a lot about during this conference, but really I'm diving deep into how water is interacting with these soils and looking specifically at soil water repellency in this area. I want to begin with a land acknowledgement. The University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. We acknowledge not only our indigenous connections and friendships, but also the histories of dispossession and forced removal that have allowed for the growth and survival of this and so many of our institutions. If you'd like to know more about the land on which you live and work, this is a great website where you can actually go and explore the legacy of your land. Okay, so from a fire and from a lot of the talks that we've heard during this conference, we can see a lot of what happens above ground. A lot of times we go to a fire location and we see burned trees, we see lack of understory, we see changes to the soil, but we can't fully understand what's going on below ground. And this is what I think is a really fun part of exploring these post-fire environments. And as we know, I mean, I'm preaching to the choir here big time, but we know that fire impacts almost all aspects of soil, from the physical to the chemical to the biological. And obviously this varies by burn severity and the temperature that those soils are actually experiencing. You know, at our lower temperature, we start to really upset our biological communities, impact some of the water within the soils. And as the temperature moves up and up and up, we start to see these dramatic changes to things like soil carbon and even the minerals within the soil. And I want to point out this little area down here in the physical portion looking at SWR, or soil water repellency. So is what we see above actually what we observe below? When we go out and we see a crown fire, 100% mortality, are we guaranteed to see something very similar in the soil? And, you know, again, preaching to the choir here, but I'm a very visual person, so this always helps me a bit. And when we think about different fire severity classes above ground, and we think of sort of their reciprocal below ground, we might start with a light surface fire, something that's just sort of moving through the understory and interacting with that soil organic layer a little bit, but not really touching the mineral horizon that much. When we move over a class to the severe surface, we start to see some scattered mortality, that fire starting to creep up our trees a little bit, and usually complete combustion of our organic matter, or at least partial or most, and maybe some impact on the soil itself. And then we move over to the crown fire, of course, lots and lots of mortality, and we end up with the soil that's almost, you know, sometimes moon dust in composition, where you walk around and you can't help but make really silly noise. At least I can't. My students find me very weird in the field, which I sort of enjoy, honestly. But I can't help walking around and being like, you know. Anytime you can bring a little bit of humor to field work is always fun. All right, so what we did first was we went out to several 2017 fires. So we have the North Peak Fire in Washington, the Millie Fire in Oregon, and then the Lolo and Liberty Peak in Montana. And we went across about 81 plots and had about 650 points where we were measuring soil burn severity and comparing it to canopy burn severity classes. And so you see canopy burn severity along the x-axis here, where we have crowned or stand replacing fire, all the way to unburned. And then on the y-axis is the percent of those plots where we found a given soil burn severity. So red being high soil burn severity, orange being moderate, yellow being low, and green being, of course, unburned. And what was interesting is that, yeah, these things tracked sort of on a, you know, when you're zooming out, you're saying, all right, well, yeah, we saw more high severity soil burn in high severity overstory fires. All right, cool, that makes sense. But what we were surprised about is that you can still find highly burned soils even in a low severity fire. So it mostly tracks. But The post-fire landscape is highly variable, which is why you're all here, because it's so much fun to study these environments, and oftentimes, mildly infuriating to study these environments, trying to understand what's going on in this incredibly variable environment. And so we can see, I love this picture because there's a little intact grass sitting over there next to this highly burned, 1,000-hour fuel log that really just scorched the soil underneath it. But understanding and predicting fire effects, particularly from a soil standpoint, is incredibly difficult at scales that matter for management. And so I'm going to focus in on soil water repellency and talk a little bit about what we saw. And I'm sure that most of you are already familiar with soil water repellency, but I wanted to give a quick overview of what happens to it. And it can be created, destroyed, or even modified during fire. So it's a very, complicated little variable in our soil, but it can have big impacts. So before a fire, we have a litter layer underlined by soil. We have our fire happening, that litter layer is combusted. Some of those hydrophobic compounds, those water repellent compounds, get moved into the soil, and as was mentioned in the previous discussion, the soil is a great insulator, so it's really good at cooling those compounds down, and as they cool, they condense onto soil particles, essentially coating them in a waxy layer and making them water repellent. And you're like, all right, big deal. So after a fire, we have some ash and topsoil and then a little bit of water repellency below. Why does that matter? Well, you can imagine if you're on a slope and you have a big rain event, right? And we're going to hear a lot about debris flows coming up here. That water infiltrates, gets that ash and burn topsoil nice and saturated, hits that water repellent layer, and everything goes careening down slope, which is bad news. And so we see this big loss of this ash and burned topsoil, which a lot of times has some beautiful soil nutrients in it to help with regeneration of plants. So it's a significant loss for the system. And soil water repellency varies significantly. And I want you to watch that first dot, and then at the end of this animation, the little dropper will come right there and go right in. Those are a centimeter apart. So this is an incredibly maddening variable to study because it is so heterogeneous with horizontal and with vertical distance. So you see a little soil profile over here that's hydrophobic at the top, and then hydrophobicity disappears down the soil profile. So it's a really fun one to study. And it's beautifully complicated. So I like to show this web diagram and then this intersection that you would pull into, and your GPS is like, I don't know, wing it, because soil water repellency is affected by so many different factors. And I'm going to focus in today on this naturally occurring water repellency and then a little bit about fire behavior. So we're going to think about burn severity. And I picked a site just for fun that already has water repellency inherent in the soil because of decomposition of the litter that's there and properties of the atmosphere and climate. So our research question is, how does soil water repellency actually vary across soil burn severity classes where there's already water repellency there? Instead of just being like, well, it was created by fire, we can now have all three of those things created, destroyed, and modified. And then how do we actually quantify soil water repellency? Is there an appropriate spatial scale? Do we have to really consider water repellency on a centimeter scale in order to understand it in these systems? And then is there anything else that's sort of pushing the patterns in soil water repellency that we're actually observing? All right, so as I mentioned, I'm looking at the Green Ridge Fire that occurred in 2020. It burned about 1,700 hectares, and it was in the Deschutes National Forest. And so this is the crazy sampling regime that we came up with. And it's a cyclical design, so you'll notice kind of patterns of spatial disparity, and then it flips in the middle and goes backward, and then it flips again and comes forward again. So this creates a very strong ability to actually predict on interesting spatial scales that are a little bit more management relevant than like, hey, you need to understand water repellency from this centimeter to this centimeter. That's not really going to go over super well. And nobody has the time or resources to look at that realistically. So each time you see an orange dot, we looked at vertical soil water repellency, so from the mineral surface down to 20 centimeters. And it looked at every centimeter, put a water droplet in, and monitored how long it took for that water droplet to infiltrate. So anything less than 5 seconds was considered not hydrophobic at all. Between 5 and 15 was mild. Between 15 and 30 was moderate. And then anything over 30 seconds, we were like, okay, we can't sit here forever. It's extreme, okay? And then anytime you see a black dot is where we also looked at horizontal variations in soil water repellency. So that little animation from earlier with the water droplets, it's an 8.5 centimeter circle, so about 50 square centimeters. And we put 14 water droplets in that little tiny space and looked at how many went in, how many didn't, and how long it took. And then we also at those points looked at soil texture, pH, organic matter, a little bit about conductance and moisture within that system. So lots of data, but I wanted to just show you, how variable is soil water repellency. So let's take at 5 centimeters depth across, and we did this across canopy burn severity classes. So we had a plot in unburned, a plot in a low severity fire, a plot in a severe surface fire, and then a plot in a stand replacing portion of this fire. So again, we're looking at the comparison between what goes on if you just went out there and you took a single point sample, so took your soil core, pulled it out, put a water droplet on each centimeter, and this is looking at 5 centimeters, versus our little horizontal grid of 14 points at 5 centimeters. So how do those actually compare? And so when we found in our vertical core at 5 centimeters that water just went straight in and we had no soil water repellency measured, that we were only right about 62% of the time. So if you had taken that soil core and measured a centimeter away, you might have gotten a complete different answer about 38% of the time. So not doing a great job at predicting when all we see is we're like, nope, there's no soil water repellency right here. When on the flip side, when we did find soil water repellency in that vertical core, we were right like 95% of the time. So it really sort of goes to show if you take a soil sample and you're like not water repellent, it might behoove you to take a couple more and double check because it's so variable. When we look down the soil profile, we know that soil water repellency is modified, created, and destroyed, and we found that when we just looked at the soil profile. So this actually shows sort of the average severity of soil water repellency, where red is more water repellent, so more toward that extreme end, and closer to the white is less water repellent. And what you'll notice is that severe surface fire, or that severe surface portion of this fire, really bumped that water repellency up, particularly between about 2 and 8 centimeters. And we generally see soil water repellency decreasing with depth, and it's strongest at less than 10 centimeters, but it's there deeper sometimes. But really the burn event at any severity decreased it right at the surface. So you see in the unburned, it's kind of darker red. As you go across at that soil surface, it's lighter red or even white sometimes. So that fire really seems to be pushing that soil water repellent a little bit deeper in that soil, which could cause difficulty for erosion events. All right, one thing I want to point out is that we did analyze and say, all right, how much of the variability in soil water repellency is actually explained by soil burn severity and canopy burn severity? And it turns out it wasn't a lot. It was like 13% of the variability. So clearly other things are really impacting soil burn severity, or soil water repellency, excuse me. So we then asked the question, all right, what could those be? And we looked at things like organic matter with the loss on ignition method. We looked at conduction, field moisture, sand, silt, clay percentages, and pH. And in general, we found that acidic soils with low moisture content, smaller particle fractions, higher organic matter, and higher conductance generally, sort of, sometimes maybe, had a little bit more soil water repellency. It didn't do a great job explaining a lot of the variance. You can see the first 2 components for our PCA only covered about 10% of variance. And for those of you who are statistically minded, you know that's really bad. Okay, so really not doing well at explaining the variability in soil water repellency. So there's a lot more to that tangled web that I showed you at the beginning than we were clearly capturing in this experiment. So there's a lot more work to be done and a lot more things that we need to understand about this really important factor that can impact big landscape things like erosion, like debris flow, like issues with water quality, issues with nutrient loss from sites and plant regeneration and successive seedlings. So in conclusion, we see these hydrophobic compounds moving a little bit deeper into the soil profile after wildfire. We see that there's small-scale variation in soil water repellency that's not necessarily scaling up very well to management-relevant scales. We see that these actual field conditions might be lost with single-point measurements, so the more we can measure, the better. As with most science, that we're always like, measure more, it'll be fun. Go out and dig more holes, go out and measure more trees. But really understanding what's going on in the entire soil environment and maybe looking at even more variables than we looked at in this study will tell us a lot more about soil water repellency moving forward. Okay, that's all I have for you. Thank you.
And we have time for a couple questions.
Yeah.
When you were
So the question was if we found any evidence of any burrowing or large-scale morbidization in the sampling areas that we were looking at, and we did not. It seemed to be a pretty tame environment in terms of, any movement by burrowing critters or any losses of like big roots that had collapsed or anything like that within the survey. We didn't see much of that. So it was actually, the field site was quite kind to us in that respect. We got lucky, I suppose. Oh, yeah, question back there.
Some fires I've been to, water doesn't go in the ground at all after a fire. Some fires, it's actually more repellent in the unburned areas than the highly burned areas. Why?
Oh, great question. So the question was, sometimes we go to a burned area and the water will pool or go right in, and sometimes we go to an unburned area and the water will actually just sit there and it'll be more water repellent. And the question was, why? Okay, so that's a great question. There's lots of different answers to that, and I wish I had like a big one that I could give you. But a lot of times you'll see, so this site had natural water repellency that was occurring because of the type of litter that was going in, and decomposition is happening, and those water repellent compounds are being released as things are being decomposed, and they sit on a soil surface as they decompose and create this lovely water repellent layer. So you can have complete water repellency in these unburned sites, and that's like this site that we chose. And obviously it wasn't 100% water repellent, but a lot of water repellency in the unburned sites. And again, we decided to toss that in there thinking, looking at soil water repellency isn't complicated enough. We're gonna do this in an area that makes it even harder. Because, we need a challenge. But so you can have this natural formation of water repellency due to those impacts. And then as that fire is burned, sometimes those compounds can be volatilized and lost via gaseous losses. So you actually end up with less water repellency in the burned area than you had before. So yeah, like I said, soil water repellency is a fun variable if you really want to go out there and challenge yourself and trying to figure out what's going on with it. It's great fun.
Kind of along the lines of that, do you ever see like large patches of soil repellency or hydrophobic soils after fire? Are there pre-fire characteristics of soils that might predispose them to repelling afterwards?
Ooh, great question. Okay, so the question was, do you see large patches? Is there such thing as a patch of soil water repellency, or is it all of this like fine scale stuff? And then what might contribute to seeing soil water repellency? Are there any sort of predispositions of a site for soil water repellency? So there are larger patches of soil water repellency, and those larger patches can really cause those bigger erosion events. And a lot of times, so the general consensus is that fire is oftentimes creating more soil water repellency than it's destroying. And so in the literature, there's a lot of papers about how water repellency is appearing after a fire and can be, quite homogeneous across the landscape. There are things that predispose a site to having water repellency. Some things, like I mentioned, having more organic matter, so more potential for having hydrophobic compounds. As those catch on fire, you may see the likelihood of forming water repellency increase a little bit. The other thing I'd like to mention too is that water repellency can change with moisture content. So if you are burning in a particularly moist fire, even if you have a standard placing above ground, if you're not combusting that material, you're not going to see those compounds start to be released or changed. So moisture can have a huge impact on soil water repellency too. Yeah. Yeah.
Hi, Brittany.
Hi.
Of course. I have a question on the plot that you're sampling with. Was it on a flat slope or was it on a side slope?
Oh, good question. So the question was, were we on a slope? Was that?
Yeah.
Okay. Yeah. So these plots we specifically chose so that they were pretty uniform in slope, and so that the physical characteristics of the site were comparable between these burn severity locations. So it took us a little while to find our plots that we liked, but we wanted them to have similar tree density, similar slopes, similar aspect, all of that kind of stuff. So we were minimizing all of those confounding factors, like as many confounding factors as we possibly could. We were trying to take off the table right at the beginning.
So they were all flat or at like a steeper 30-degree angle
We actually lucked out and found pretty flat ground, like slope less than 5%.
Do you think that you would see any kind of, maybe like increase in patch size with slope, or like if you have more like similar erosional processes happening? Because I feel like on flatter forested regions, maybe you get like some microtopography.
Yeah, so good point. So thinking about flat surfaces, thinking about microtopography, might you see more uniform behavior on a slope versus flat ground? That's a great question. So I also think it has to do with fire burn severity, what you see on slopes versus flat. A lot of times when the fire is not on a slope, it can kind of take its time moving across the landscape, so you might get more uniform burn severity versus on a slope where it's kind of moving quickly and might interact with the soil in very different ways as it moves up that slope. So you may end up actually seeing more heterogeneity on a slope than you would on a flat surface. That's just sort of an off-the-cuff kind of thinking about that, but it's certainly microtopography, especially for a variable this just dynamic. It definitely makes a difference. And like I said, we quantified as much as we could while we were out there, but it was a pretty intense sampling regime. But yeah, we tried to capture as much of that variability as we could, but certainly more work to be done, as always. Yeah. All right, thank you.